Hello, we're going to talk about topic 1.8, determining limits using squeeze theorem. Okay. So in this little box, I have a definition that we're going to use today. And ultimately, it involves a compound inequality. So I have a graph here to kind of assist with what this is talking about. So if you have a function g, and you are able to sandwich that function between two different functions, f and h, right? For some interval about, in this case, it should be, excuse my typo here. This should be an A, not a C. And you know that the limit as x approaches a for the function, the smallest function, is equal to the limit as x approaches a of the largest function. If those two limits give you the same value, then the limit of the function in the middle has to also give you that value. Okay, so if your small function and your big function give you the same thing, then the one in the middle has to follow suit. Okay, so that's kind of the idea here. So we're going to take a look at this example here. Example 1, determine the value of the limit as x approaches 0 for this x squared sine of 1 over x. Okay. Now looking at the graph, you know, the x squared sine of 1 over x is this red function, and it's going to kind of oscillate, and it's going to kind of go up and down. But as I get closer and closer to 0 from the left and from the right-hand sides, because it's a two-sided limit, you can see that my function is decreasing. It's getting closer and closer to that x-axis. And ultimately, using the graph, I am led to believe that this limit, sine of 1 over x, is probably going to be 0, okay? But the goal is we're going to try to prove that algebraically and not just guess from looking at a graph, okay? Now, I am going to use my calculator here. I've kind of pre-calculated some numbers, so you might need to take your calculator out and find some of these values on the calculator. But what we're going to do is we're going to take, if you look at this graph, I have this function sandwiched between x squared and a negative x squared. And if you notice that x squared is always greater than the red function, and negative x squared is always less than the negative, less than the red function. So, and I know that because ultimately sine of 1 over x is just going to kind of oscillate between 1 and negative 1. So when I do this, I'm going to complete this table of values. So as x squared, if I plug in negative 0.01, I get a 0.001. I get a 0.12341. Okay. And then I have a 0.1234561. And if you plug 0 in x squared, you get 0. Now, this will be symmetric. So if I do the same calculation on the other side, you'll get the same values, which is kind of convenient. All right. And using our previous topic of evaluating limits using table of values, we know that x squared from the left and the right is going to get closer and closer to the value of 0. Now, I am going to do the same thing for down here. If you do a negative x squared, that's just going to give you actually the same values, just negative. So I'm going to write those in there. There we go. All right, and you can see that this limit is also going to approach 0 from the left and from the right. So we want to prove this algebraically, right? We want to prove that this limit is going to be 0 using some mathematical logic, all right? So here's what I'm going to do, is I'm going to say, to start with, x squared, or a negative x squared, is less than or equal to x squared sine of 1 over x, which is less than or equal to a positive x squared. So I know, and you can see from that graph, that that function is going to be sandwiched in between, okay? Now, if I use limits, all right, if I take the limit as x approaches 0 of a negative x squared, right? I know that that's going to have to be less than the limit as x approaches 0 of x squared sine of 1 over x, which has to be less than the limit as x approaches 0 of a positive x squared. Now, we just used the table of values to prove, and you probably didn't need a table of values, but if I take the limit as x approaches 0 of a negative x squared, okay, that's just going to give me the value of 0. Get my stylus working here. Which is then less than or equal to the original problem. And we know that this is 0, right? So if you have two things or two limits going to 0 and they're on either end of this compound inequality, you know that the middle limit has to be the same value. That's the only possible option. So I can make a conclusion here that based on that, as x approaches 0, of x squared sine of 1 over x has to be 0. Okay, so that's kind of my logic here. So for part D, I just want to practice using the definition of squeeze theorem to kind of write a verbal sentence. Okay, so I'm going to start with if let's see if I can get this to write here. Okay, if a negative x squared is less than or equal to x squared sine of 1 over x, which is less than or equal to x squared. And the limit as x approaches 0 of a negative x squared is equal to the limit as x approaches 0 of a positive x squared, which is 0. Then the limit as x approaches 0 of an x squared sine of 1 over x has to also equal 0, right? So we have our hypothesis, right? We have our conditions. We know that this function is sandwiched in between these two that we know. And then we can then show that those two limits are equal to the same value, in this case 0. And then we can prove what that limit is actually equal to. So that's how we're going to verbally state our limit expression with the squeeze theorem or sandwich theorem, okay? Now, I have two more examples here. I'm going to go through them. Feel free to pause, fast forward, whatever you need to do, okay? But I want to go through these two examples, and then we'll kind of continue on with some sandwich theorem. So in this case, I have the limit as x approaches 1, very similar to the problem we just had. And what I know is that when you have the sign of any expression, okay, I'm going to start here. So the sign of anything. Now if I have any function, right? I know sine always oscillates. If you know anything about a sine curve, it's always going to oscillate between -1 and 1. Now it might have a different period, or it might, not necessarily be consistent throughout that period. But I know that it's not going to go outside that range. So with that being said, I know the smallest it can be is going to be the -1 from the sine times the other piece of my expression, which in this case was x minus 1. has to be less than or equal to the original piece and I know that's going to be less than or equal to a positive 1 times the x minus 1, right? So I know that that original function that's inside the limit has to be sandwiched between those two values. So now all I'm going to do is I'm going to take the limit as x approaches 0 of a negative 1 times x minus 1. And if you do a direct substitution, that gives you 0. And then I'm going to do the limit as x approaches 0 of a positive x minus 1. And if you do a direct substitution, that also gives you 0. So then we can conclude, I'm going to use the 3 little dots. Therefore, the limit as x approaches 1, oh, I accidentally mistyped or miswrote. Feel free to make that correction. I apologize, guys. This limit is going to 1, not 0. Thinking one thing, writing another. Sorry about that. If I take this limit as x approaches 1 of the original function, pi over x minus 1, I know because it's sandwiched in between these and they give me the same output that this also has to be 0. Okay? So that's the idea. One more, same idea. Okay? So if I do this, again, cosine works very similar to sine. Cosine, again, is going to oscillate between 1 and negative 1. So if I do this, I can start with a statement simply saying that if I do a negative 1 times 2 to the t minus 1 has to be less than or equal to the cosine of 1 over t, which is less than or equal to a positive 1 times 2 to the t minus 1. And you have to show that inequality in order to use squeeze theorem, or if you call it sandwich theorem, that's fine. And if you're going to use squeeze theorem, you have to show that inequality. So now we can set up our limit expressions. So if I were to take the limit as x approach, or not x, but t, sorry about that, t approaches 0 of a negative 1, 2 to the t minus 1. And if I plug a 0 into that, I'm going to get 2 to the 0 power, which is anything to the 0 power is 1 minus 1 is 0. So this having some stylus problems, bear with me. There we go. So I got a 0 here. And then if I take the limit as t approaches 0 of the positive side, so 1, 2t minus 1, if that equals 0, then I can make the conclusion that the limit as t approaches 0 of, oh, I forgot my 2t minus 1 in this. That should be in there. Of cosine of 1 over t times 2 to the t minus 1. Trying to use good notation all the way through, guys. Okay, I know that that's also going to have to be 0. Okay, so that's my conclusion. But you have to state the preliminary conditions. 1, you know the function, the inequality, the compound inequality. 2, that you can show that the outside limits are equal to the same value. And then you can draw your conclusion of what that middle limit will be. Okay? So if you look at example 3, what does squeeze theorem say about the limit as x approaches 7 of f of x if the limit of L of x and the limit of u of x is 6? Now, if you look, okay, and I'm going to kind of focus your attention, the green one is u, the blue one is L, and if you look, the red is sandwiched in between them. So because you know that f of x is going to be between L of x and U of x, you can conclude that the limit as x approaches 7 of f of x is also going to be 6. Okay, that is an okay conclusion. Now, for part B, though, it says the inequality f of x is less than U of x is not always true. It's not satisfied for all x. Does that change anything? So if you look over here, all the way on the left, you can see that the U and the F, they cross, right? So I can't say that F is always smaller than U, but that doesn't matter. I just need it over some interval to the left and some interval to the right. It doesn't have to be a big interval. I just need to prove over some interval, left and right, of that point of interest, that entire interval, that compound inequality is true. Okay, so does that affect our validity? No. Okay, we just need a little bit to the left and a little bit of that, a little bit to the right of that point to have that compound inequality be true. Okay. All right. So I put a couple problems in here. So I have a function, I have a table, I have a graph. College Board makes a big push to kind of make sure you can mix different representations together. So what I want to do for part A is I want to find the limit as x approaches 2 of s of x. And I'm going to kind of circle here. This compound inequality is very, very, very important because it shows you the progression of these functions, okay? So if you know that inequality is true, right, I want to find the limit of s of x as x approaches 2. So what I'm going to do is I know s has to be sandwiched between t and one of these two functions. So I know that first s of x is going to be less than or equal to t of x. Now the question is which function p or r do I want to use for the left-hand side? Well, I'm going to start with saying that the limit as x approaches 2 of t of x, right? Start with the one that we already know. If you look at this graph, as you approach 2 from the left and from the right, it is a two-sided limit. That is going to give you a value of 5. So now I want to take a look at p and r. Which one of those functions will give me a limit of 5? Because again, in order to use squeeze theorem, we need the left and the right of our compound inequality to give the same output. So if I do this as x approaches 2, of which function will also be 5? That's what I want to look at. And if you take a look here, okay, that's going to be r of x. So I'm going to say r of x, and I want to finish off this compound inequality. So we have r of x is less than s, which is less than t, and we proved that both of those limits of those two functions is going to be 5. So now we can conclude that the limit as x approaches 2 of s of x has to also be 5. Okay, that's the idea. All right, same idea. I want to do it for 0. Okay, so if I do this for 0, again, t has got to be the bigger one. So I know if I do s of x, I know that's got to be less than or equal to t of x. We're going to figure out which one they use, but I'm going to start with what I already know. So as this goes to 0 of t of x, and I'm going to look at the graph for t, from the left and from the right of 0, that graph is going to 9, right? Now, r of x at 0, well, the table doesn't really give me that information. That doesn't really help me for r. So what I am going to do is I'm going to use p, and I'm going to kind of fingers crossed, hopefully, this limit will also go to 9. Okay, so if I look at this function, it's a negative 7 to the x plus 10. So I'm going to say a negative, I'm going to do a direct substitution, a negative 7 to the 0 plus 10. Okay, Now, if you do anything to the 0 power, it's going to be 1. Now, the negative is not raised to the 0. It's just a 7. So I get a negative 1 plus 10 is then equal to 9, which is perfect. That's what I want. So now I can draw the conclusion that the limit as x approaches 0 of s of x will also be 9. Okay, so that is squeeze theorem, or otherwise known as sandwich theorem. The key points here are that you can find a function that is bigger, right? So I'm going to write on my work here, bigger and smaller, so we can create an inequality, and then we can show that the limits of those two ends of my compound inequality are the same value, and then you can draw the conclusion for the original problem that was given. Okay? Hopefully this helped. Contact me if you need anything.